So speed and velocity, we'll go quick on this one. We've seen from year 9 that the speed equation, speed, is equal to the distance travelled, divided by the time taken. So everybody should be pretty au fait with that. We can put it in a triangle. So in physics, they like to make you rearrange for higher grades, so kind of from level 6 onwards. So being able to rearrange is a real advantage. And in this one, we can remember it as small, tiny, d at the top. I don't know why I put a tail on that. It doesn't have a tail. So small and tiny, d at the top. So that's the first thing. If you leave with anything, that's the one. Now, if I was to plot this out, I could plot out a map and I could draw where I've gone, like so. And I could have a start and I can have an end. And the distance would be this bit along here. So I could get a ruler, a bit of string, a trundle wheel, and I could measure that. And that would give me the time. Now, this is a form of a number called a scalar. A scalar. You may have come across this in mathematics. A scalar is a number with magnitude only. Magnitude. Oh, something went wrong there. Dude, only. What that means is, think of the number as a circle. 1. If I draw the number 2, 2 is bigger than 1. Number 3, 3 is bigger than 2. And it seems obvious when you say it that way. 1 is obviously smaller than 2. So in this case, when we write down this distance, say a distance of 10 meters, it's just a size. And so when I've written this out, I've got a scalar number. Now, why am I telling you this? If we took this same one here and we did it as the crow flies, by that I mean in a straight line directly from start to finish, and we measured that line, I'm going to call this the displacement. It's all about how far away you are from where you started. I started there, I ended there, and let's say this one is a distance of 5 meters. Well then, if we use that number, displacement over time, what we're actually going to calculate is called velocity. So you'll have heard people use the word velocity and speed interchangeably, but at a technical level they're two different things. So velocity is the displacement over time. And you'll end up with a different number. There's something else about velocity as well. I can draw an arrow showing that I've gone from one place to another, which means that displacement is a vector. A vector. Now a vector is a number with magnitude. Number, okay, I really can't spell, I've been off school so long. Number with, I'm just going to put mag, and direction. So what does that mean? Well, that means if I told you the number 2, I could draw an arrow that represents the number 2. I could write an arrow. I could draw the number 4, I would make the arrow longer. 4. I could also draw -2. I just draw it backwards. And vectors are unusual in that if I had two scalars, 2 add 2, I get 4. Whereas if I was to add these two vectors together, I'd get 0. So vectors in this example are the displacement and the velocity. So surmising this, we have the speed equation. Speed is distance over time. That takes the distance, which is a scalar, divides it by the time and gives us a number for speed called a scalar. If, though, we look at as the crow flies, we measure the displacement from where you started to where you ended, then what we get is velocity, and velocity is a vector. So that's the first thing. Now, why does that matter? Well, it matters for a number of reasons. If you were air traffic control and flying around you were planes, it's pretty handy to know where the planes are, where they're going, how fast, when they're going to land. So here we've got a typical plane, like so. If you were flying in, air traffic control can't see you at the moment, and you just report your speed is 500 miles an hour. You've told them a scalar. What you're lacking in your description is your direction. Where are you coming in from? So pilots will not use speed as an indicator. What they'll use instead is they'll state their velocity. They'll state how many miles per hour they're going, 500 miles per hour, but they'll also add on to it the direction they're coming from, and in this case, southwest-ish, southwest-west. That means immediately the air traffic control can see where that person's coming from. The other thing is, and this one's a bit of a quirk of mathematics, imagine I've got the running track. So we'll draw, made it disappear, try again. There we go. We've got the running track, and the distance of the running track is 400 meters. The start and the finish line are both at the same line. We couldn't afford new paint. So the start and the end are exactly on the same line. So the displacement is, hopefully some of you can say it before I say it, 0 meters. And you run it, you huff and puff as you run round, and you do it in a time of 100 seconds. You're not fast, but the numbers are easy. So you do it in 100 seconds. So the question now is, what was the speed? What was the velocity? And we end up with two really strange answers. Well, one's strange, one not. So let's work out the speed. We'll do the distance divided by the time. So we'll do 400 meters divided by 100 seconds. So that's nice, because it gives you 4 meters per second. No shocks. This one, though, is weird. Velocity. The displacement. Now we've got a problem. I can't put D for displacement because distance has already nicked it. So we put an S, a little s, which is a pain in the bum because S usually means speed. But you'll see it written in books as little s. So displacement. Our displacement is 0 over 100, which gives us 0 meters per second. Isn't that weird? But here's the reason why. Imagine you were floating above in a drone, and every second you took a photograph and you drew the direction of the person. They started there, they ended there. They started there, they ended there. And you had all 100 arrows drawn, 100 seconds. Well, if you remember, I said to you that if you add two, let me take this one. If I add this vector to this vector, I get, so a down, add, an up, I get 0. And if I take this vector here, so let me get my yellow again, and my orange. If I take that vector and that vector, I have one vector going this way, a vector going that way, add them together, I get 0. And every single vector has an equal and opposite vector. One here, one there, one there, for one there. They all cancel out, and when you add them all up, you get an average velocity of 0. So it's not to say you're not moving, but velocity doesn't care where you've been. It only cares where you started and where you ended. And I think that's the end of the first lesson. Now, the page number, if I had it in front of me, page will be attached I'll put a full copy of the book in the messages, in the notes area, and I'll also just take this page alone and put it in. So I'd like you to make sure you've copied the notes. You can either write them and pause this as you go, or you can just copy them straight out of the book, which would be neater. Then please make sure you've either taken a photograph of your work and attached it, or if you've done it on a Google Sheet, Google whatever doc, just attach it. And if at worst comes to worst, just please put that you've done it and click done, because I'll have a nice little list and I'm able to track how everyone's getting on. Okay, take care. Bye bye.